Okay, so the topic of my two lectures are focusing on singularities and blow up in what are called viscous Hamilton Jacobi equations. And of course, please stop me if anything is not working. Okay, so now let me explain a little bit what I will discuss in this today and tomorrow. So the main example, the main model is the following second order equation, which contains first order term. So here, this is time derivative of u, and this is the Laplacian of u. And here we have first order terms, which I will simplify essentially into the model case. So the first order terms are essentially functions that will be coercive and superlinear. And this is why, I mean, the power example, the absolute value of the gradient of the solution to the P is the model example. Okay, does not need to be exactly that, but this simplifies, of course, the presentation. Everything is set into Rn and specifically in a bounded domain, which is smooth. And the focus will be on what kind of phenomena can affect the evolution, the long-time behavior, when we do have Dirichlet boundary conditions. Okay, so we are in a bounded domain, and the point is what can happen in case of Dirichlet condition does not need to be exactly equal to 0, but again, this will fix a reference case. It could be a different function, but the point is that there are conditions on the boundary. And actually, the functions f and u0 are given data. And I want to stress immediately that, of course, you could reverse the sign of the nonlinearity if you change u into minus u. This would simply bring the equation into this form, and then you would find the nonlinearity somehow as sort of a reactions term or sorts term. Unless we make assumptions on the sign of the solution or the sign of the data, which I won't make, the two problems are equivalent. Okay, but of course we need to fix the ideas. So at this time I will start essentially by dealing the case with nonlinearity in the absorption part. And all the point of this short course is that even if f and u0 are smooth, singularities may and will appear. And this is an effect of the superlinearity. And as a general rule that is given in journalism, when something happens, when there is a fact to report, we should try to explain. I mean, in Britain, they say the 5W. Here, I just have 4. These are what happened, where it happens, when, and why. And the 5th would be who is the responsible, but then you will see it a little bit in the story. Okay, so first of all, I want to mention why those are called the viscous Hamilton Jacobi. Okay, viscous refers to the Laplacian, but what is more important is to recall the motivation. Motivation comes from stochastic control, and this is why the Bellman dynamic programming and the Hamilton Jacobi name comes from. So this is the interpretation of the solution. So the interpretation is the following. So you take this, now this will be the prototype equation. So you have this power on the left, the u to the p. You have Dirichlet boundary condition, an initial value. And you can represent this might be formal but can be made rigorous, U as an infimum, so as a value function of an optimization problem, and this is a dynamic optimization over a stochastic trajectory. Stochastic because precisely we have this Laplacian here, and so this means that there is a Brownian motion in this dynamics. So you may imagine that the dynamics is just two terms, a sort of deterministic part with a drift, and a diffusion part with a Brownian motion. And both are stochastic processes, and you imagine to use the drift as a control to realize some goal. The goal is to minimize a certain cost functional. So this cost has two parts. This running cost as a part which is a given cost f along the trajectory, and there is a cost that you pay for using a certain control. And this is a power of the control, and in particular is the conjugate exponent of the exponent p that you observe in the equation. And the running cost occurs between 0 and the first moment you exit the domain. So the dynamics starts in the domain, and then there is an exit time, and then you have to consider only up to the exit time. And of course, if you have not yet reached it somehow, if the dynamics is still inside, then you, if you stop at time t before the exit time, then there is another cost to pay, which is given by the initial term. So this is a representation formula, but in some sense it will not only motivate but also give some explanation of why some phenomena are observed. It's important in this story of representation that if U is the somehow optimal value, what's more important in optimization is the optimal strategy. And the optimal strategy would be the optimal control, the optimal drift is somehow the linearization, if you want, of the nonlinearity here, depending on the U to the P. So this is up to the minus sign. This is, oh, I'm sorry, I probably need to close the email, otherwise it will bother me. Okay, so, and so it's important that the gradient of U is associated to the given optimal strategy in feedback form. Okay, so to be clear, all the first lecture will be devoted to the stationary problem. So it's very important to understand the stationary problem, and then tomorrow I will talk about the evolution problem. Why? Because we need to understand what kind of phenomena happen and also why they happen. And so let me start by the stationary equation. So the stationary equation, there is something you can observe immediately, which is that due to the superlinear character, since p is bigger than 1, superlinear and coercive, the existence of solutions may be lost. A very easy example in the quadratic case shows that if f is too negative, then you cannot have any solution to this equation. This is easy to observe through the off-call transform. So we have a privileged case, which is the quadratic case, because the very model equation can be transformed into a linear one. If you take the quadratic equation here, quadratic nonlinearity, then by the exponential classical transform, v is e to the minus u, it is transformed into a linear problem. And then we all know that for this linear problem, of course, first you observe that if f is too negative here, well, of course, this will be beyond the first eigenvalue, and then there couldn't be any solution because, of course, I mean, if you observe the sign, then this should be some, I mean, obstruction to the existence of a solution, because if f is negative, u is negative, then v is positive, and so on. You can be more precise, in fact. You can say that a solution exists if and only if the first eigenvalue of this linear operator is strictly positive. So the stationary problem in the quadratic case is very clear, but even in the non-quadratic case, you have some obstruction, quite clear. So for example, you may multiply the equation by a test function, a function which is C infinity with compact support. You multiply, you integrate by parts, and you use Young's inequality. So the recipe is very simple. You multiply by a test function, you use Young's inequality, and then you observe that you have this inequality which must be satisfied by the function f. Okay? And this involves the conjugate power of phi, the gradient of phi, with some weight. You can see that this is at the same time a size constraint, so f minus cannot be too large, and also a regularity constraint, but this is more subtle. But of course, it has something to do with capacity, with the p prime, actually capacity, as you see from here. And I won't enter into this fine regularity constraint, which is developed in many papers by Mazia, so in particular in the Russian school. And it's in particular developed for this equation in Ansen, Mazia, and Verbitsky in 1909. So essentially, this regularity constraint is sort of capacitary constraint that f minus must satisfy on any compact set. But get rid for a while of the regularity. So assume that f is smooth or simply L infinity. Then you can characterize the solution, the stationary solution. This was a result I gave in some years ago, 2010. For the subquadratic case, you take a bounded f, and then there exists a real number C0, such that, in fact, the stationary problem admits a solution if and only if this number is positive. So clearly, this is the extension of the first eigenvalue somehow I mentioned in the quadratic case through the change of unknown. There is no change of unknown here for general P, but yet there is a constant which plays the role of kind of first eigenvalue. And also you can observe that if you add any positive lambda u, lambda positive in the left, which is, of course, now close to what we will observe in the evolutionary problem tomorrow, then there is always a solution for a bounded f, but this only for p smaller or equal than 2. So what is called the natural growth, say not exceeding the energy gradient square of the Laplacian. So essentially, there are several things that play a role in this story, and the first lecture is mostly devoted to understand the role of those things on the stationary equation. So one is the threshold of superlinearity, p bigger than 1. One is the threshold of natural growth, which is p equals 2. And p bigger than 2, we could call it supernatural growth, or maybe unnatural, because we will observe some phenomena which are not completely consistent with what happens with p smaller than 2 and what happens for the second order equations. But I will discuss it later. Then there is a crucial role played by gradient bounds, because of course a nonlinearity is here on the gradient and on the behavior of what will be maximal solutions. And then, of course, this sort of eigenvalue C0, which I mentioned before, this constant, where does it come from? And this is, of course, kind of notion of additive eigenvalue. Okay, so it's very, I would say, important to start from the bounds, the gradient bounds, and this is a very classical story, which, by the way, originates somehow with the Russian school, with Bernstein method, and then those gradient bounds were extensively developed by James Serrin, and also then revisited in particular for this kind of equations by Pierre-Louis Lyons. So what I'm referring to is the following estimate. You take any solution of the equation, you don't know anything at the boundary, and any solution satisfies an estimate inside which depends on the distance to the boundary. Of course, it also depends on the right-hand side, but assume that f is bounded, which is the easiest case. And also the bound may depend on lambda u norm infinity. But what is more important is where this estimate comes from. And this is a very straight application of the idea of Bernstein that the gradient square of a solution of, say, a second order plus type equation is a subsolution. So you see, this is first inequality is typically the inequality which estimates, this is actually an equality, to be honest, and this is an estimate, if you want, or the equality which says the Laplace operator on the gradient square of u. So this operator has two contributions. So one is the Hn to the square, and the other sees the derivation of the equation and then along the direction of the gradient of u. And then if you use Young's, by the way, this inequality is such intrinsic that it's even true in Riemannian manifolds, and it's called the Weizenburg formula, and it's also with the addition of a term which considers the curvature of a manifold. So here we are in Rn, so it's flat, and you don't see this curvature term. So it's a very important intrinsic equality in this case, or inequality in general. And if you use the Hilder inequality or Cauchy-Schwarz, you see that this dominates the Hn square, dominates, you see this term, dominates the Laplacian square up to a constant. And then you can use the equation, you reinject the equation, and then you have this term here when you have taken the derivative. So here you take the derivative of the equation, and then you see the gradient of f. You see here the term with lambda, and you see the gradient of the nonlinearity, okay? And then these first three terms here, these first three terms, they all come from the first term here, when you take the gradient of the equation along the direction of, say, the gradient of u. But you also have this extra coercive term, and you reinject again the equation, and you see you get this extra term, and this term is coercive because essentially dominates the power of the gradient to the, say, to the power twice p. Okay, so it's somehow dominant in this situation because p is strictly bigger than 1. So if you take the new function, which is the gradient square, this will be a positive subsolution of an equation, which is second order, as a lower order term due to lambda, as a transport term here, which comes from the linearization of the nonlinearity, and because of that Hn square, you see a superlinear power of W here, and this is a subsolution against something which involves F, involves a sublinear power of W which can be dominated. So in fact, as you learned, observed, of course, in the talk by Laurent Veron, since P is strictly bigger than 1, you have local bounds for this kind of equation. Local means that you have interior bounds independent of the boundary behavior. If you scale the argument appropriately, you get, of course, also the precise power of the distance, and you may have seen that, I'm sure you have seen that in the talk, in the lectures by Laurent Veron. And so the gradient actually is dominated by this negative power of the distance. Okay, so let me see the consequences of that. There are many consequences and all are important to be underlined. Well, of course, the first one, there are solutions. The solutions may satisfy that the gradient blows up at the boundary, but at the same time, they remain controlled inside. And this means that the Neumann problem admits maximal solutions that blow up on the boundary. I want to mention immediately that the estimate is an estimate on the gradient. So the question is it stable for u or u? Essentially, it only depends on the L infinity norm, not on u, but of lambda u. So this leaves room for the limit when lambda goes to 0, because u could even blow up itself, but multiplied by lambda, it can remain controlled even when lambda goes to 0. And the estimate on the gradient would remain stable. So we also observe that there is a huge difference between p smaller than 2 and p strictly bigger than 2. Why? Because this power of the distance is integrable if and only if p is strictly bigger than 2. So this would immediately lead to an integrable singularity for the gradient and therefore a bound, an L infinity bound for u. So this will make a big difference between the two regimes, subnatural growth, say up to 2, and supernatural growth. Okay, another remark. One could, of course, even use this kind of estimate on annulus. For example, you could localize even in external domains. And for example, you can do that just to deduce interior singularities. I won't talk too much of that, but I will mention it later in the end today. Okay, and finally, those local bounds of the gradient could also be global, say up to the boundary for the Dirichlet problem, provided of course, you find a boundary barrier. So if you find a boundary barrier to estimate the gradient at a boundary, then you can use the same inequality on the Bernstein method to have a global bound. In fact, this was pointed out by Lyons in the 80s in a very general framework to say that the existence of a solution, at least say for a reasonable, smooth solution, the existence of a solution is in fact equivalent to the existence of a Lipschitz barrier, actually a sub-solution. Why it is only important a sub-solution? Well, because this is due to the, in this case, to the sign of the nonlinearity, because u, since this is positive, u is always a sub-solution of the Laplace equation. So actually a super solution exists easily, and this is just the solution of the Poisson problem. So the super solution is for free. What the problem is to find a sub-solution which can make the role of a barrier. And this is why the existence of a solution can be equivalent to the existence of a Lipschitz sub-solution. Lipschitz because the gradient would be bounded and then would play a role of the barrier at the boundary. Okay, so what are those maximal solutions? I mentioned that the Neumann problem has maximal solutions. So let me now say what are those maximal solutions. And as I try to explain, there is a big difference in the threshold p equals 2. So let me discuss thoroughly the case that p is smaller or equal to 2. And these were studied by Lathree and Lyons in a very important and pioneering paper in the 89. The typical result is the following. Give me lambda positive. By now, lambda is strictly positive. F, okay, I'm not entering into the case that f is singular, so f will be bounded in this story for me. And there exists a unique solution, which is sufficiently regular if you want inside, C1 alpha at least, and C2, if f was C0 alpha, you would be C2 alpha inside. and this solution blows up at the boundary. This is in fact the maximal solution of the equation in omega, and satisfies some singularity at the boundary, which is precise. It's a logarithmic. If p equals 2 is the log of the distance, this is the log scale of the Laplace after Hopf-Call. Okay, and in the other cases, for p between 1 and 2, this is of power type. Okay, so 2 minus p prime is negative if p is strictly smaller than 2. Okay, so p prime is always, for me, the conjugate exponent here of p. Okay. There is an interpretation in terms of the stochastic control problem. So, in fact, u is the optimal value for what is called the state constraint problem. What is the state constraint problem? The state constraint problem is the problem where the process, in this case, the stochastic process, is kept inside the domain for all times, so that the exit time is infinity. And in fact, you can say that putting an infinite cost at a boundary, or if you want the maximal cost which is possible at a boundary, means that somehow you would like not to reach the boundary. So somehow this means that all the strategies you are considering are used to keep the process inside the domain. But of course, to constrain a Brownian motion not to leave the domain, you need to push at a boundary, infinitely strong. And this is why, of course, you will see the singularity at a boundary. Okay, the proof of this result is not difficult, to be honest, because you have seen things like that, I'm sure, in the lectures by Laurent Baron. You start by taking the value n at a boundary, solve a standard Dirichlet problem, and then let n go to infinity. So you build an increasing sequence of solutions. You build explicit sub and super solutions in terms of the distance function, a little bit maybe shifted with 1 over n. And then this gives local bounds and the asymptotics of u when n goes to infinity. So you will behave like this negative power. I'm somehow dropping the case p equals 2 when everything is with a log. So it's slightly different. But the spirit and the proof is the same, of course. Then you also have the local gradient bounds I mentioned. So you have strong compactness inside, and then you find the existence of solution. And uniqueness, in fact, depends on the precise asymptotics that you got before. Here, the argument of uniqueness is, again, very typical of boundary blow-up solutions. If you know that U1 and U2 have the same asymptotics that you can prove by sub and super solutions, then you may just perturb a little bit one of the two solutions in a way that at the boundary this will be below U2, and you use maximum principle, and you prove this inequality, and then you let epsilon goes to 0. Okay, of course, there are some mild variations. You may use this kind of convex combinations here because the nonlinearity is convex. Otherwise, you may just perturb a little bit the solution, one of the two solutions with this singular, say, reference nonlinearity, solution, and so on. But this is very typical. What Lathree and Lyons also studied is the limit when lambda goes to 0. Again, you just observe from the sub and super solutions that, in fact, you can be a little bit more precise than my previous estimate. So any solution, in fact, satisfies estimates of this type, which means that if you multiply by lambda, lambda u lambda, in fact, is locally bounded. And since lambda u lambda is locally bounded, the gradient bounds I have shown before, they are robust, meaning that the gradient of u lambda can be still estimated in terms of a negative power of the distance. And then you see this means that lambda u lambda necessarily need to converge to a constant locally uniformly because if the gradient of u lambda is controlled, when you multiply by lambda, the gradient of this function will go to zero. So this is a function which is locally bounded, and its gradient is locally converging to zero. And so actually, this up to subsequences, it converges locally uniformly to a constant. And this constant, let me call it C0, is the first time we see appearing the constant I mentioned at the beginning. Of course, you can create also a limit function. In which way? Well, the gradient here is controlled inside, so you just fix any point x0 inside, and you just consider the translation u lambda of x minus u lambda at some point x0. And now this is a function. Its gradient is locally controlled, and this takes the value 0 at some point. So, of course, this will be locally bounded and also locally relatively compact. And it converges, in fact, to a solution of this problem where you see lambda u lambda is going to this constant C0. It is less obvious that you still keep this boundary blow-up condition, but this is a consequence of the nature of the estimate near the boundary. So near the boundary, so you see it's not by chance that somehow near the boundary, everything is very robust. Okay, in this kind of result, this is the result by Lasry and Lyons, what is less obvious but more it's more deep is the uniqueness of this constant. So there is only a unique constant for which this problem has a solution, and also the uniqueness of u up to the addition of a constant, because you see in this problem you can add any constant to u. U is invariant by addition of a constant, and but still you have uniqueness of u, and this is due to the strong maximum principle. So in fact, this is a statement for the case lambda equals 0. There exists a unique constant C0, which, so it is just depending on f and the domain omega. So there exists a unique constant for which the problem admits a solution. And the solution is also unique up to addition of a constant. Okay, I won't mention now why this is called the ergodic problem. This is related, and I will explain a little bit tomorrow, related to the evolution problem, to ergodicity somehow. But I will just recall that for p equals 2, C0 is in fact the first eigenvalue after the off-call transform. And this uniqueness of u up to addition of a constant is just the simplicity of the first eigenvalue in that case. Okay. Okay, as I already mentioned, later, much later, when I needed this result for the long-time behavior of the evolution problem, I just observed, this was not, too difficult, but I just observed that, in fact, this constant C0 is precisely what characterizes the solution of the stationary problem. So you have, first of all, a representation of C0 as the supremum value for which you can find subsolutions. And again, this is reminiscent of the characterization of the first eigenvalue a la Beresticki, Nirenberg, and Varadhan, as the supremum for which You may have, depending on the sign, say sub or super solutions, positive in that case, okay? And okay, and then the Dirichlet problem. So you see, admits a solution if and only if C0 is positive. And in particular, we also observe what was the spirit of the result by Lyons, that a solution exists if and only if there exists subsolution. Here we observe that you don't need a Lipschitz subsolution, but just a bounded, actually, subsolution. In this is because P is smaller than or equal than 2. And when P equals 2, as I already said, this is exactly the first eigenvalue of minus delta plus F, a Schrödinger type problem. Okay, I want to now discuss a bit more the singularity at the boundary. And this is something we proved with Laurent Baron in 2006, that the gradient singularity is somehow consistent with the estimate for the U, and there is a first order asymptotics of the gradient which goes in the normal direction. In particular, the tangential component of U is a little o of the normal component, which we stressed at that time is just one way to observe kind of off lemma for boundary blow-up solution. So in all boundary blow-up solution problems, you could somehow wonder whether this kind of off lemma holds, that the tangential blow up is in any case of smaller order than the normal blow up. The proof of our result was just by scaling, was not too involved, it was simple. You have the gradient bounds, and then you have the first order asymptotics for U, and then you can do a blow up. Say U delta is just a rescale. You see, you fix a point x0, which might be on the boundary, and then you make a blow up around this point, and you define the blown up equation for U delta, and this power is exactly what makes the equation for U delta of this type. It's an equation like minus delta U delta plus, this is the scaling of the nonlinearity is correct, and all the other terms scale in a way that they will disappear when delta goes to 0. But because of the gradient bounds and because of the asymptotics of U, you know that U delta is bounded in Lipschitz norm. And therefore, you just use elliptic regularity. U delta is compact in C1 alpha, and it converts to a one-dimensional solution. One dimension, of course, this C is oriented in a way that, say, this first component, for example, is just directed along the inner normal from x0. Okay. In fact, this shows that the gradient of U has exactly the maximal blow-up rate after, say, Bernstein type estimate in the normal direction. And this is consistent. This is somehow the optimal feedback strategy that constrains this Brownian motion inside omega. In fact, the analysis of this boundary singularity can even go further and show other phenomena which might be interesting, because in this boundary blow-up problems, usually, typically, the first asymptotics is one-dimensional, just depending on the distance. But the second asymptotic, the second order, the second term is geometrical and should take into account the d operator on the boundary, and the Laplacian of the distance shows curvature effects. This was very nicely pointed out by Bandel and Marcus for other boundary blow-up problems. And then with my former student Leonori, we discussed this issue, and we showed, in fact, with a little bit more of regularity on F, we showed a second order asymptotics for the gradient. Actually, here I have just put this statement, and not exactly for the, of course, we have a similar statement for the gradient, but it's more interesting for what is the optimal feedback, which is just the gradient roughly to p minus 1. And this behaves exactly like the reciprocal of the distance with some precise constant, p prime. Of course, it pushes inside. It pushes inside. This is the control. The control pushes inside and the gradient goes outside. And the second term is exactly proportional to the mean curvature at the projection point of the boundary. And this is still in the normal direction, while the tangential direction is always negligible when p is strictly smaller than 2, or at least bounded when p is equals to 2. Okay, it might be interesting to just to spend a couple of words, since we are talking now at this moment, now really we are talking about analysis of singularities. It might be interesting to discuss a little bit where this result comes from, because now this is an interesting consequence of a sort of linearization of the equation around the singular solution. So the idea is you take a singular solution. What is the singular solution? It's the reference behavior of the maximal solution. This is singular now. And then you linearize formally, if you want, the equation around this solution. And then the gradient u to the p, you develop. And the first term that you observe is this type. And then you have the remainder, which is quadratic, of course. And then somehow the linearization means that you consider the u minus the singular solution. This is function v, and you observe that a little bit formally, but typically it solves an equation which is similar to this equation here, which is, of course, the linear term is still linear. This is the linearization somehow of the nonlinearity, which is here developed, say, in like Taylor expansion. This is the first order and this is the second order. And the first order, you see, it behaves like a vector field divided by the distance. And this vector field is tangentially negligible. And normally, this vector field normally is coercive and is strictly, coercive in the normal direction. And then we proved this kind of regularity result for this kind of equations, where you use the coercivity of the linear drift term. So assume that you have a linear drift term where the field B is pointing in the normal direction strictly bigger than the diffusion constant. So it's dominated the diffusion and it's tangentially negligible. And then any bounded solution is Lipschitz. So this is a kind of regularity that you start with bounded and you end up with Lipschitz without knowing anything at the boundary. And you prove a posteriori that there is a Neumann condition at the boundary. This is probably something that, at least I would say in the Russian school, should sound familiar, because somehow this is just one version of kind of problems discussed in Russia by Oleinik and in Italy by Fichera, of problems where usually you can rephrase this problem by multiplying by the distance. You build the degenerate problem, and in this problem you might have some part of the boundary, in this case all of the boundary, where you don't need to put any condition because it's the equation that is bringing itself the information. And this is what happens here. And our results, in fact, of course, are more general than linear, but this is the prototype. And the main technical tool is once more to go back to the Bernstein's idea in a weighted now version. So by weighting the equation of the gradient square, this is now weighted with functions of the distance. You develop the same kind of computation I did at the beginning for the first equation. And now this is again a sub-solution, but because of this weight, you create a zero-order term in the equation of this auxiliary function. And this zero-order term is precisely helpful depending on the linearization of the, say, the Hamiltonian of the first-order terms along the normal direction. So it's a kind of a Hardy type. You see first-order term independence of the distance to the boundary, and then you can get extra information. And this is what we developed with the Leonori at that times. Okay, and then of course, if you prove that this guy is bounded, then this means that U is Lipschitz, and if U minus some singular solution is Lipschitz, this gives you the second order term in the end in the expansion. Okay, so now, okay, let me now go back to the case that P is strictly bigger than 2. This is a very different case. And when P is bigger than 2, I already mentioned, if you just follow the gradient bounds, then this exponent is now smaller than 1. So U should be bounded. In fact, U turns out to be globally bounded, and even Hölder continues up to the boundary, which means that you cannot expect any singularity on U if not observed on its gradient. So how to express the boundary condition is the first thing that Lasry and Lyons wanted to make clear, and they used an idea from viscosity solutions. The idea is that if formally you would expect U to be maximal, say formally infinity, then you can just say that in fact U minus any smooth function cannot have any local minimum attained on the boundary. So this is a typical approach in viscosity solutions to observe the local minima of U minus phi. Or the idea, this means that you cannot expect phi to touch from below U for the maximal solution. And you can also rephrase this information by saying that U is a super solution on the boundary. And if you want to give sense to that, because U will be, the gradient will be singular, so you cannot give sense to that, I mean, classically. So this means that in viscosity sense, the equation, holds, I mean, not the equation, but the super solution condition holds up to the boundary. This is the kind of statement in the same paper by Lasry and Lyons, F bounded, lambda positive, there exists a unique solution, which inside is the same regularity as before, but now U is not blowing up, it's just a super solution on the boundary in the viscosity sense, and this is the maximal solution and is globally Hölder continuous. U is still the value function of a stochastic control problem with state constraints, so absolutely the same interpretation. Why? Because in this problem, what really cares is that the exit time is infinity. And in fact, even if U, the cost, U is the optimal cost you have to pay, even if this remains bounded, you still need to prevent the Brownian motion to go out, which means that the exit time is infinity, and so the admissible control must be singular. Except that it's now much more delicate to show the singularity of the gradient of U, because it cannot be obtained by scaling from U. So this is a completely different proof to show the singularity of the gradient, and this is very recent. I have to say that we came back with Philippe Souplé very recently on this question to show exactly the same kind of singularity for the gradient that we had proved with Laurent Veron with the P smaller than 2. Now this is true even for P bigger than 2, but we needed a new ingredient, and this new ingredient was still a blow-up technique, but actually a new Liouville type result for maximal solutions on the half space. So now we don't rely anymore on what we know on U, but we somehow do the blow-up, and then we have to prove a sort of a rigidity theorem on the half space. That's what we prove with Philippe Souplé here. And this also extends some ideas that were developed by Philippe with Roberta Filippucci and Patrizia Pucci some years ago, actually. Okay, then the limit when lambda goes to 0 of the maximal solutions was also studied by Lasry and Lyons. So you can say again that even if P is bigger than 2, there exists a unique constant for which this problem has a solution, and the solution is unique. So there is again this constant C0. Again, the constant C0, actually, if it's positivity or not, again characterizes the existence of solutions to the Dirichlet problem. But this is very important. Now, this Dirichlet problem cannot be formulated classically. Why? Because there may be a possible loss of boundary conditions. So now the problem needs to be formulated in a suitable sense. Because recall that the solution of this kind of equations, when p is bigger than 2, they, in fact, are Hölder continuous up to the boundary. And this is completely independent of the boundary data. Also, there is a global universal bound for u plus. Oh, sorry, in this case, this should be probably for u minus. I must have switched. Oh, no, sorry, this is for u plus. Okay. And so all these things that happen independently of the boundary values means that there are size and regularity conditions that are needed for the boundary data. So you cannot prescribe any boundary condition. So in fact, what you can do here, if you want to solve the Dirichlet problem, you must admit that the boundary conditions can be relaxed. What does it mean? Well, this is what people do in viscosity solutions theory. And actually, that's also what people do in first-order problems. You cannot prescribe in first-order problems, you cannot prescribe always boundary conditions. And so sometimes you admit that the boundary condition is generalized. What does it mean? It means that, for example, here, U, as I already said, U is always below the Poisson potential of F, so U will always be smaller than 0. But it can be that U is strictly smaller than 0 at the boundary. So if U is strictly smaller than 0, this means that U must be a super solution up to the boundary, because one of those two must be non-negative. Either U is itself non-negative, and in this case, if U is non-negative, then this means that U is 0 at the boundary, because U is certainly always smaller than 0 at the boundary. So this condition, in this case, should be read that either U is 0 at the boundary, or U is strictly smaller than 0, which can happen. But in this case, it's the equation that is non-negative at the boundary. And with this generalized notion of solution, the Dirichlet problem now admits this generalized solution, if and only if the constant C0 is positive. So you can observe the same kind of result, but in this generalized sense. Okay, so if, okay, I guess I started a little bit later, so I don't know how much time you want to allow me.
2 minutes.
2 minutes.
2-3 months. 2-3 minutes, but no, we will more not so strong.
Okay.
Let us be more generous. 5 minutes.
Yes.
Okay.
I agree.
Thank you. I will try to sketch a little bit some comments and extensions a little bit more. So first of all,
some questions, but you have remembered that some question from the audience maybe.
Okay. So first of all, I mentioned already that the same kind of singularity may be analyzed in the interior. Essentially, Lyons did that already because of the Bernstein estimates, essentially. But also, these singularities may be responsible of possible loss of uniqueness. There's a typical example, a radial example. This is exactly not by chance the singularity we had before, but now at a single point, say the origin of the ball. You take the unit ball, you take the singularity, and then you get a distributional solution of this equation, okay? Mm-hmm. And in particular, this is even in H10 if P is above a certain threshold. And even, Okay, of course, when p equals 2, you have to use the log, okay? So in particular, you observe that uniqueness may even fail in H1 0 if p is above this threshold. But also the same example also holds for p bigger than 2. So if you observe for p bigger than 2, 2 minus p prime is positive. So this is a continuous function. Hilbert continuous, however, not Lipschitz. And it's still a distributional solution. But it's interesting to notice is that the Hilbert function in this case is not a viscosity solution because it has a singularity which is of, say, not consistent with the definition of viscosity solutions, okay? And by the way, there is no problem of uniqueness if you are below this threshold of n over n minus 1. Okay, you have some recipe to recover uniqueness. One of the recipe is to use stronger solutions, but you have, of course, to prove the existence of those solutions. Stronger means that you require the gradient to have the right integrability for the linearized problem. So this would be that the gradient of u should be in Ln p minus 1. And the spirit is that if you linearize the nonlinearity, you see this term should be in Ln. I mean, this is well known for people in elliptic theory that in the first order term, linear type, if the drift is in Ln at least, then you may have maximum principle and well-posedness. Okay, but this can work for P not too big, thanks using some result by Boccardo and Galouet. And this may work in general P, but you need to use Calderon-Zygmund estimates. And this is what, in particular, was developed by Marco Cirant and Alessandro Goffi, the Calderon-Zygmund estimates for this kind of equations, meaning that if this operator is in Lm, then both terms lie in Lm. This is the typical, say, W2P estimates or Calderon-Zygmund. And this is in some deep results that were recently proved by Cirant and Goffi in the recent years. With Guy Barre, we also gave another alternative to a recipe to recover uniqueness, which was to use solutions such that a suitable power, maybe a superlinear power, is in H1 rather than not only U in H1. And when P is bigger than 2, as I said, somehow it's like first order problem. So you need a viscosity solution theory, and you need somehow to go to viscosity solutions. And this was developed in many papers. Okay, so there are extensions to P Laplace equation, but I'm not sure I do have time to mention here, and also to general first order terms. These are mostly developed with my former student, Tommaso Leonori. I just want to, if you want, of course, I can say more, but I just want to say that the summary of this first lecture, which I will also recall tomorrow, is that we have seen that at the heart of this kind of equations, there are local gradient bounds. And then we discuss how this gives rise to maximal solutions. Those maximal solutions generate an additive eigenvalue for the first time. But then this additive eigenvalue characterizes completely the solutions, the existence for the stationary problem. So it will not be a surprise that when tomorrow we want to look at a long-time behavior, then we will see how the singularity of the maximal solution, how the additive eigenvalue, everything comes into play when we want to understand, of course, the evolution in time. Okay, so I stop here, and of course, if you have questions, you're welcome.
Nice. Thank you very much. Alessio, some question maybe. What I will use my singular position. What in this part, when you spoke about infinite boundary condition for this equation with gradient nonlinearity. It was, in some sense, parallel or familiar to the study of large solution for equation with nonlinear absorption. Asymptotic of large solution near to the boundary.
Yes.
Looks like this one. This also a paper of Marcus some Bendel about asymptotic process. But in this context, what connection may be as to result? You know, for example, this theory of large solution is a question about uniqueness of large solution. Here, is it possible to answer whether such solution is infinite value boundary is unique or not? First question. But I don't know. Maybe you know.
Yes. Yes.
Yes,
Okay.
It is unique. Unique.
So
and second question. Yet one question. Because you spoke about linearity gradient of to the power of p. But for absorption nonlinearity, people consider all general nonlinearity, f of u. If you will have f of gradient of u. And a very important role in absorption nonlinearity plays some limiting nonlinearity, which allows to have such a solution. Keller-Rosserman condition on the growth.
Yes.
Whether here it is maybe theory of such equation with non-power-like nonlinearities, with, for example, like an analog of Keller-Rosserman. What such two questions which generated by absorption of nonlinearities? What you can say?
Okay. Thank you. So I take both questions, and the first one is about uniqueness. So in the result by Lathree and Lyons, they already proved uniqueness of these boundary blow-up solutions for smooth domains. So the answer is sufficiently clear. In case of smooth domains, comparing to what was analyzed in many papers by Laurent Veron with Moshe Marcus for the semilinear case, well, the situation with non-smooth domains is is still widely open here. I mean, there are not.
I know, of course. I kept in mind such a regular case of domain.
Yes, for smooth domains, if indeed these maximal solutions are unique, these boundary blow-up solutions are unique. This was already in the Lathree Lyons.
What year when it was proved? How?
It was proved already in the original paper by Lathree Lyons in '89. And then we came back a little bit on this question, so you might also have an update, and this answers your second question. With Tommaso Leonori, we came back a little bit to a general somehow situation.
So any condition.
Exactly. So suppose that, as you were asking, the nonlinearity is just any function, say, of the gradient. So here we also analyze that for the P Laplacian when P is, at least when P is bigger, of course, if also equal to 2. And
if P is 2, then it's linear linearity.
Exactly. So you may read this for P equals 2, and of course it's fine. And so this is a general function H. And so you see the threshold of the superlinearity is what you would expect. So this is the threshold for having the local bounds, which replaces somehow the Keller-Rosserman that you were mentioning. And with this threshold, you know that the Neumann problem admits maximal solutions. So this means that there exists a function such that the gradient blows up at the boundary and that the operator stays bounded. Then there is another threshold which would correspond to the threshold of natural growth, say P equals 2. And this threshold is the following: is still an integral threshold, and the difference is that in one case the barrier, so that the maximal solution blows up itself. So not only the gradient but also the function blows up. And this means that the barrier can be chosen as large as desired, and this means that the Dirichlet problem is solvable somehow, provided just you do have any sub or super solution. Otherwise, if integral condition is violated, is not satisfied, this means that the maximal solution which exists, the gradient blows up but is integrable, and the U does not blow us up. And in this case, you are a little bit like in the case where you might have loss of boundary conditions, and you should more be in the field of, say, viscosity solutions or things that are degenerate problems. So if you want, there is this is a kind of scheme. So you will, of course, find that in my slides, that you can read it for P equals 2 if you want. That I'm sorry, because the P, maybe I should change that before sending the slides, that this P is not the same P as, as before. Yeah, as before. And so you see that there is this would correspond to the Keller-Osserman when you do have local estimates, and then the maximal solution also blows up, and in this case the maximal solution does not blow us up. So this is the answer to your question, essentially.
Very interesting, delicate question, a delicate answer. Very nice. Thank you very much. Thank you. Yet question, what additional question?
I have a question. Okay.
Please.
Yes. My question is something that probably you know that I've worked on it, is to assume that the boundary you have 0 except one point, a singular point. What happened?
Okay, so again, once more, those cases of isolated singularity. Well, if you really take one point on the boundary, this is likely to be removable in many cases, I guess, but
not always.
Not always, sure, not always. And because, of course, you know, I mean, your older result with Gedda says already cases where you might solve for this kind of equations with direct mass at a boundary. And so it's clear that it's related to that. But I would say that in general, so the analysis of the boundary singularities, but even if blows up in a part of the boundary and does not blow up in another part, so what you developed with Moshe extensively for the semilinear case is still largely, completely, I would say, almost completely open in this situation. I mean, because the problem is that the singularity is mostly brought from the gradient, which means that it's quite tough to use comparison arguments for the singularity of the gradient. And this explains why probably this has not been developed too much. But this doesn't mean that at least partial results should be probably available. And but the answer is that is absolutely a direction which has not been exploited, to be honest.
Well, there are some results that I prove with yes,
of course.
degree and flock tie.
Sure. Yeah, some so results that you also have proved with your student.
Characterization, yes.
Sure. In fact, I think that I mentioned your result with Gedda for the direct delta, but then you refined the.
It's not Gedda, it's Gmira.
Gmira, sorry, it was Gmira, sorry. But then, as you were mentioning, your most recent result were probably are the only that I know on that.
Yeah. Colleague, maybe somebody would like to ask.
We have a written question from Lev Yegorov.
Okay.
Lev, would you like to say it in words?
Maybe I can find it.
Okay, I can just read it.
No,
Thank you for your talk. Is there some results for H depending on X, U, and du? At least H is equal to a function A of XU times du.
It can exist.
Okay, cases of. Okay, so of course, I mean, one can imagine that the sum of two functions, one depending on u and one depending on the gradient.
Yes, this is the main example.
Yeah,
Yes,
of course. No, yes, but this is probably the easiest one can imagine. Then you can superpose a little bit the talk or what Laurent Veron described on the semilinear case with this case, and there will be, depending on which nonlinearity is leading or so the case of the sum of two contributions, so one in U and one in the gradient, I cannot say that has been completely developed, but I would say that it's quite reasonable. There are results that I have in mind. One was by Bundle and Giarrusso, and probably many other people later have worked on that, I'm sure. But your question probably is even, I mean, more demanding. Maybe you want to know in the product of nonlinearities of U and nonlinearities of the gradient, what could happen. And this is less clear in my mind. Of course, I think that everything still should come from local estimates. And then, again, you might decide in the local estimates whether you want to control U just by sub and super solutions, or whether you have the control on the gradient through the Bernstein method. The Bernstein method can also be used in wide generality, but you can even, there are many versions of Bernstein's method where you, rather than using just the gradient U square, you use a more involved function of U and the gradient. So I would say that the methods that we described, I'm saying we because you have seen methods surely in other talks in this school. I would say that the methods are certainly available even when the nonlinearity is the product maybe of U and the gradient, but I do not have results to tell you straight away, and probably there might be interesting cases that I'm not sure maybe if they have been underlined or pointed out. So I must say that the references I mentioned are absolutely not exhaustive. There are many others, and probably I was waiting to have a little bit of time to put a list of references more complete. So I'm certainly also missing probably other contributions, but straight away I don't have, I mean,
just to mention things that which is an interesting case is when you take a nonlinearity, which is a difference between the term of UP minus grad U to the Q.
Okay,
and there is a very interesting balance between the two terms. This is something we did with a little with Marie-Françoise.
Yes, you're right. Yeah.
Alessio, yet one remark. But really, if the absorption term A of X, F of gradient U. But in absorption term situation, it is for uniqueness play a role behavior of this potential A of X near to the boundary. If it is degenerate very fast, uniqueness may be lost. But it is not completely clear question. But what influence on uniqueness plays such a potential A of X? But maybe it is in gradient nonlinearity, uniqueness also will depend on such a degeneration of potential A of X.
Yes.
Such a remark.
Yes, I mean, I'm sure you're right, because of course this localization phenomena and the singularity, everything depends on this first order of this nonlinearity, which dominates somehow the diffusion. And clearly, if you somehow put some coefficient depending on X, which switches off the role of the nonlinearity, or it's clear that it will have an impact. I totally agree with you, yes.
Notice till now it is not clear. really whether it plays or not plays, because for in absorption term, if some exponential generation only there is some gap. It generate like exponential with some with Gini condition. Then uniqueness is. If not, then may be absent. Not clear. Not as I understand, it's not the end. It depends on geometry of domain omega. If the domain like circle, Laurent gave some example. If domain is like circle, like a ball, then not. The asymptotic does not play a role. If the geometry is another one, it may be such a situation for the absorption nullarity. Here for gradient nullarity situation is much more complicated, I guess. Mm-hmm.
Yeah, I totally share your viewpoint, and I think that when I showed the first estimate by Bernstein method, you have seen, here you have seen the analogy with a semilinear case. So this is the model computation where from this starting equation, the gradient square becomes a sub-solution of a semilinear problem. So it's clear that what you are saying means that certainly if you know already something for this problem, it will also have an impact here. That's sure.
Yeah. Very nice. Very nice. Very interesting question. It's so problematic. Some circular questions, and this the direction of investigation very interesting. Not closed till now. It attracted attention. Colleague, some question. Whether we can continue discussion?
Okay, I have a last question, maybe. Do you know something, for example, if you replace your domain by a cone, a regular cone?
I don't know.
Can you expect something? It's regular. You assume that it is regular.
Yes, you know, Laurent, you know better than me that probably what you would try to do is to write solutions in this separable form and maybe try to.
It could help, of course.
Yeah, sure.
Laurent, you mean finite cone, some non-regular point? Yes. What you
Just
mean?
a cone.
Yeah, I don't know.
One point is like conical point on the boundary. Yes.
Well, conical, it's too complicated. Just a cone. It's very simple. So it's explicit. It is explicit in some sense.
Yeah. I don't know of results, but doesn't mean that there could have been.
It could be interesting to look at that.
Yeah. I think that all the questions on boundary singularities in domains which are not smooth in this context, I think that they are really have not been really touched.
Yeah. Yet questions?
Probably yes.
Please.
Boris Andrianov asks, is something known in unbounded domains?
What the last question was about this one? Infinite cone.
Half space.
Well, yes, there are results, and of course, this estimates which in particular I do have here on the screen. In particular, if you use those estimates in external domains, but even in the whole space outside the ball, this says something on the behavior of the solutions at infinity. And then, of course, something that will play a role is the behavior of the source f at infinity as well. And so, there are results, and in particular, they have an impact on the large time behavior. So tomorrow we'll discuss the role of those solutions in the long time asymptotics of the evolution problem. The results that I have in mind on the unbounded domains are mostly, I've come across those results in particular for results of the evolution in unbounded domains, and then they needed to characterize the solution, the stationary solution, as well in unbounded domains. So there are results which have similar flavor, but of course are more delicate because of the infinity. For example, typically this uniqueness of this constant, I try to explain, this is a first eigenvalue. And you know very well that in unbounded domains, the question of the first eigenvalue is already much more delicate. So you can imagine that the situation, I mean, has a similar flavor, but it has more, I mean, more difficulties, but there are results. So there are people, of course, I can mention, there were results by a Japanese Ichihara. There were results by people from stochastic control somehow, like Sheu, and also Guy Barles worked on a lot on that, on unbounded domains with other collaborators, Alexander Klaas and others that work in viscosity solutions also have worked on that. But probably there are, of course, much more. Marie-Françoise Butoveron has worked a lot also on unbounded domains, maybe okay, on other aspects, but in particular, she has worked a lot even in unbounded domains, also for the evolution problem. So, of course, the questions, one should also look at the precise maybe question one has in mind, and then I would say that people have looked at unbounded domains, and what I discussed today has been studied, and the situation is a little bit more involved. There are other aspects that also may have been investigated, in particular by Marie-Françoise or others, more related maybe to the evolution, but also to the existence, for example, Liouville type results. There are many also contributions on that which are related a little bit to this story of singularities. I mentioned Philippe Souplé, its works, but of course, again, Butoveron, Marie-Françoise has worked also a lot on that, with Laurent also as well. So here, of course, so I don't have, I mean, on my eyes this literature, but it's not difficult to gather this kind of contributions.
Yes.
I don't know if Laurent wants to say more, or Marie-Françoise wants to say more on that.
Today, it's okay.
So somebody would like to continue our conversation?
I think we can speak of that tomorrow, no?
Yeah. Tomorrow, yes. No, we'll do some rest, yes, maybe. So, on the treatise is dark, absolutely. So around me, it is evening.